So there's a lot of material for today, and that's unfortunate, but it was necessary to get everything in this very short period of time. So the rest of today's material has to do with sort of the debris in our solar system, and that would be the asteroids, the comets, and of course poor little Pluto. So the reason that we're interested in comets and asteroids is because those are really sort of the building blocks that would formed our planets. You could think of them as the planetesimals that never got to be part of a planet. And so it gives us clues into what was going on in the early stages of our solar system. Early stages of formation of our solar system. So the asteroids would be the rocky remnants. Those would be basically within the frost line, while the comets would be the icy remnants, things that we find out beyond where our out beyond the frost line and even beyond where we see the planets. And so basically we're looking at those because it gives us clues to the beginning of our solar system. We are probably familiar with the fact that the main place that we find asteroids is between the orbits of Mars and Jupiter. There's this big sort of gap that seems really kind of unnaturally large. Sometimes people say, oh, well, maybe there was a planet that did form in that area and Jupiter's gravity tore it apart. This is highly unlikely. The more likely scenario is that Jupiter's gravity actually probably prevented a planet from forming in that area, which would then explain why there's such a large gap. When you think about our solar system, basically the big players are of course the Sun and then Jupiter because of its very large size. Also, you might notice that there are some clusters of asteroids found along Jupiter's orbit, and those are called the Trojan asteroids. There's also asteroids that do pass within the Earth's orbit, and some people worry a lot about those. Will they ever hit the Earth? And it's always possible, but we don't know. It doesn't seem likely, at least in the near future. So you see that while they're concentrated in a certain area, they're found in a wide range of areas. The other thing that's important to kind of understand here about this asteroid belt is when it's sort of depicted in this picture, it almost looks solid, but there actually is quite a bit of free space between individual asteroids. So it would help understand how our spacecraft that we send out into space to study the outer edges of our solar system, they can actually travel through the asteroid belt pretty easily. One of the things that we do see within the asteroid belt is sort of these resonance gaps, and I ask you to sort of remember what we learned about with Saturn's rings. And at certain locations between Mars and Jupiter, there really is sort of an absence of a large amount of asteroids, and that's because, again, that has to do with a gravitational resonance between the orbits of those asteroids and Jupiter's orbit. And so these ratios here are talking about how many orbits of Jupiter compared to how many orbits of the asteroids. And so what happens is, because it's a pretty simple relationship, the pretty simple fractions or ratios, those asteroids would pass by Jupiter fairly frequently, and Jupiter would be able to successfully pull them out of that orbit, and that's how it happens. So that's another example, again, of what we would call gravitational resonance. The way that you can find asteroids is you can look for sort of a streak in the sky if you take a picture, because the star's motion is going to be so much less noticeable in the short time of picture exposure than that of an asteroid. That has to do with its close proximity to us compared to the very far away distance that the background stars are. And so essentially you can take pictures and look for these streaks to find asteroids. And this is something that an amateur astronomer could do pretty easily. These are some pictures of what asteroids look like. Notice they are heavily cratered. Also notice their irregular shape. Because they're relatively small, they don't have enough self-gravity to pull themselves into a spherical shape. So they maintain sort of this lumpy, amorphous shape that you see in these pictures. So now we're going to move on and talk about comets. Comets are going to be the icy leftovers for our solar system, but we don't want to compare them to shooting stars. They're not the same thing. A shooting star is a meteor that enters into the Earth's atmosphere, and as it burns up with the friction with the atmospheric gases, you see the streak of light. But those are very short-lived. I mean, if you've ever seen a meteor, you know you see it streak and then it's gone. Well, if you are lucky enough to see a comet in the sky, comets are actually visible in the sky for periods of weeks, if not a month or so, and they move very slowly, but they do have this sort of pretty appearance with the long tail and so on. The way to describe a comet in terms of what makes this beautiful picture that we see here is the object itself is like a dirty snowball. It's a big chunk of ice with a lot of other dirty compounds in it so that it looks actually rather dark. And what happens as it gets closer to the sun, it starts to basically the ice starts to melt and vaporize from the sun's heat when it gets closer to the sun, and that material starts to surround that dirty snowball, and eventually it forms into this picture that we see here. This is a picture of a comet that was seen in the mid-90s, and this actually is a nice picture because it shows you sort of that intermediate stage where the comet hasn't developed a tail yet, but you can see that there's a fair amount of material that has built up around it as this comet has neared the sun, and its frozen material has started to vaporize and collect around that nucleus of the comet. Here's another picture of a comet that has the more traditional appearance that you might think of with the big tail. And also notice here that there are actually two separate tails, and we'll talk about what causes those. So what is the comet? Let's talk about the different parts of it. First of all, we have the nucleus, and that's what I talked about that we could call the dirty snowball. It's actually very, very small, probably only a couple kilometers across, which means that if the comet wasn't vaporizing, we would never be able to view it because it would be much too small to see even with a big telescope. As the nucleus nears the sun, the material starts to vaporize, and it surrounds the nucleus, and it forms what we call the coma, which is sort of the round area around it. Then we also see the tail, which is sort of the material that gets pushed out from the nucleus and forms a tail of material, and those can be actually very long, up to an astronomical unit in length. Here's actually a picture that astronomers were able to get in a very opportunistic way when another satellite was close to Halley's Comet. And notice, this is a picture of the nucleus and how dark it is. And you see these bright areas right here where material vapor is coming out from it as it nears the sun. This is sort of this is obviously a drawing of what the Halley's Comet looked like, the nucleus, and you see the jets of material coming out. What was sort of surprising was how dark the surface of Halley's Comet was. It truly was a very, a dirty snowball for sure. The fact that these jets could form, because what could happen is the surface might just crack and vapor comes out of that, will make the orbit of the comet maybe a bit unpredictable, because they really will act like small little jets that can propel the comet nucleus a little bit and maybe alter its orbit slightly. Here's a picture of Halley's orbit compared to the orbit of the Earth, and notice that while we know that the planet's orbits are ellipses, The orbits of comets are much more eccentric ellipses in that they're very much longer and skinnier, so that when they're far away from the sun, their distance is very far away, and then they come in and get much closer to the sun than the Earth's orbit. Here's another picture of an orbit, and also here we talk about the different tails. There's two tails that a comet forms, and it's actually the tail. You might have assumed that the tail would trail behind the comet as it went around its orbit, but the tail always points away from the sun because two different things that the sun does and interacts with the comet form two different tails. The dust tail is basically just the uncharged, dusty material that comes off of the comet as it starts to vaporize, and that's actually pushed by the solar radiation. Literally, light can exert a pressure, which is kind of a weird thing to think about, but if you think about photons, you might be easier to understand that that would be possible. So the dust tail gets pushed out by the sunlight. The plasma tail, which is charged particles, gets pushed out by the solar wind, which is also charged. And so these don't always match up with each other because of the two different things that are causing it. Notice also here you can sort of see how the comet changes during its orbit, and how, you know, as it gets in closer to the sun, you start to see the vaporization begin, and it gets very distinct tails when it's very close to the sun, and then as it goes away it starts to fade out again and then just becomes a little hunk of ice orbiting the sun. Here's another picture of the two tails of the sun. Another thing, we already saw that the orbits of comets don't always lie in the plane of the solar system. They also can, we saw that they were very elliptical, or very long and skinny, but they also can sort of be very random. They can come up from below our solar system or come down from above. They don't have to lie in the plane of the solar system like the other planets do. Here's another picture even showing Halley's Comet is tilted relative to the orbit of the planets. And once again, showing you the eccentricity of Halley's Comet, just to give you a sense of what they look like compared to the orbits of the other planets. And so we're going to stop here, and we'll begin with the next video talking about where comets come from.